The Foundations of Geometry by David Hilbert. Chapter 2. The Compatibility and Mutual Independence of the Axioms. Section 12. Independence of the Axiom of Continuity, Non-Euclidean Geometry. In order to demonstrate the independence of the axiom of Archimedes, we must produce a geometry in which all of the axioms are fulfilled with the exception of the one in question. For this purpose we construct a domain, omega of t, of all those algebraic functions of t which may be obtained from t by means of the four arithmetical operations of addition, subtraction, multiplication, division, and the fifth operation, the square root of 1 plus omega squared, where omega represents any function arising from the application of these five operations. The elements of omega t, just as was previously the case for omega, constitute an enumerable set. These five operations may all be performed without introducing imaginaries, and that in only one way. The domain omega t contains therefore only real single-valued functions of t. Let C be any function of the domain omega t. Since this function C is an algebraic function of t, it can in no case vanish for more than a finite number of values of t, and hence for sufficiently large positive values of t, it must remain always positive or always negative. Let us now regard the functions of the domain omega t as a kind of complex numbers. In the system of complex numbers thus defined, all of the ordinary rules of operation evidently hold. Moreover, if a and b are any two distinct numbers in this system, then a is said to be greater than or less than b, written a greater than b or a less than b, according as the difference c equals a minus b is always positive or always negative for sufficiently large values of t. By the adoption of this convention for the numbers of our system, it is possible to arrange them according to the magnitudes in a manner analogous to that employed for real numbers. We readily see also that for this system of complex numbers, the validity of an inequality is not destroyed by adding the same or equal numbers to both members or by multiplying both members by the same number, providing it is greater than 0. If n is any arbitrary, positive, integral rational number, then for any two numbers n and t of the domain omega t, the inequality n less than t certainly holds. For the difference n minus t, considered as a function of t, is always negative for sufficiently large values of t. We express this fact in the following manner. The two numbers 1 and t of the domain omega t, each of which is greater than 0, possess the property that any multiple whatever of the first number always remains smaller than the second. From the complex numbers of the domain omega t, we now proceed to construct a geometry in exactly the same manner as in Section 9, where we took as our basis of our consideration the algebraic numbers of omega. We will regard a system of three numbers x, y, and z of the domain omega t as defining a point, and the ratio of any four such numbers u, v, w, and r, where u, v, w are not all 0, as defining a plane. Finally, the existence of the equation xu plus yv plus zw plus r equals 0 shall express the condition that the point xyz lies in the plane u, v, w, r. Let the straight line be defined in our geometry as the totality of all points lying simultaneously in the same two planes. If we now adopt conventions corresponding to those of Section 9 concerning the arrangement of elements and laying off of angles and of segments, we shall obtain a non-Euclidean geometry where, as the properties of the complex number system already investigated show, all of the axioms, with the exception of that of Archimedes, are fulfilled. In fact, we can lay off successively the segment 1 upon the segment t an arbitrary number of times without reaching the endpoint of the segment t, which is a contradiction to the axiom of Archimedes. The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Wrenholt. Programming and illustrations by Jim Wrenholt. 2019. Portrait of David Hilbert by Reida Wrenholt. Thank you for listening.